Hi, and welcome back. My name is Steve Miller from Williams College. This is the continuation of the Teachers as Scholars lectures. And what we're going to do is we're going to continue with our stuff on cryptography and RSA, and we're going to start with Fermat's little theorem. So you might be familiar with Fermat's last theorem, which is, just so it doesn't take up as much of my video. Okay. So you may be familiar with Fermat's last theorem, that if you have x to the n plus y to the n equals z to the n, and x, y, z, and n are integers, and n is at least 3, then the only non-stupid solution is, there are no non-stupid solutions. You can only solve it if x, y, or z is 0. Fermat's little theorem, with a lowercase l, is very useful for a lot of stuff in cryptography. And so we talked earlier that phi of n is the number of integers from 1 to n relatively prime to n. So we showed that if you take a prime, then phi of p is p minus 1, because every number will be relatively prime to p. And if we took a product of two distinct primes, then it's just p minus 1 times q minus 1. We don't need, but there's a lot of properties about this function. You know, this is the bare bones. What do we absolutely need to get to our goal? Do not be distracted by all the wonderful theory, which is hard for me to do, but I will just put a placeholder here and ignore it. And so here's Fermat's little theorem. It says, take two numbers, a and n, and assume they're relatively prime. Then if you raise a to the phi of n, you get 1 mod n. So if you have a clock with n hours, a to the phi of n would line up with 1. We only need two special cases for what we're doing. We need the case when n is a prime, p minus 1, and we need the case when it is a product of two distinct primes. So whenever you have something like this, you can have the students do some tests, see if this is reasonable. Take some values of a and n and check and see, does it work? So I'm going to prove it first in the case when n is a prime. So again, n is a prime p. We'll assume that the greatest common divisor of a and p is 1, so a and p are relatively prime. So I'm going to consider the numbers 1, 2, all the way up to p minus 1, and I'm going to multiply each number by a. So we have a, 2a, 3a, 4a, and so on. So we have two sets of p minus 1 numbers. And for each of them, I can look at what is their remainder when I divide by p. So which side is easier to look at remainders when we divide by p? The left one's 1, 2 to p minus 1, or a, 2a, all the way up to p minus 1 times a. Which one of the remainders easier to understand when we divide by p?
The left one.
The left, right? Because the remainders are already there. It's just the numbers 1, 2, all the way up to p minus 1. The one on the right, it's a little bit harder. I claim, however, that the sets are the same, that both sets, the remainders are just 1, 2, 3, all the way up to p minus 1. What that means is that there's no repeats in the second set. So imagine there were. So imagine two of these numbers are the same. Let's say I times a is the same as j times a on our clock. So they have the same spot, so it means that their difference is a multiple of p. Well, we can subtract, and we get I minus j times a is 0. So that means p divides I minus j times a. But p doesn't divide a, because a is relatively prime to p. So p must divide I minus j. So that means I and j are the same hour. They just differ by a multiple of p. Well, we can't have that because our multiples I and j go from 1, 2, 3, all the way up to p minus 1. The largest difference we can have is if I is p minus 1 and j is 1, and that difference is p minus 2. So we can't have I equals j. So all the residues are different. So because they're all different, if I multiply these numbers on the left and I multiply these numbers on the right, they will differ by a multiple of p. So when I multiply them, this multiple is just going to be p minus 1 factorial. This is going to be p minus 1 factorial, but I'm also going to get an a to the p minus 1 because each term also has an a. So these two numbers differ by a multiple of p. But p doesn't divide p minus 1, P doesn't divide P minus 2, P doesn't divide P minus 3. I can cancel this P minus 1 factorial from both sides, and so I get a to the P minus 1 has to be the same as 1. And so that's the proof. You can modify this argument for the general case. I prefer to do the following trick. And this is just a really nice math concept. So imagine we have n equals the product of two distinct primes. And we'll assume that A has nothing in common with P and Q. One of the best descriptions I've ever heard of what is a mathematician is a lazy person. Never do anything that you don't have to. Whenever possible, reduce whatever you are given to a previously solved problem. One of my favorite jokes is a mathematician and an engineer walking down a street, and they see a house on fire, and there's a fire hydrant in front of it with a hose disconnected. The mathematician connects the hose, turns on the hydrant, and puts out the fire. A little bit later, they walk and they come to a house that's fine with a fire hydrant in front of it with a hose that's connected. The mathematician disconnects the hose and sets the house on fire, reducing it to a previously solved problem, and then continues walking down the street because I've already solved that. Whenever possible, whatever you're given, find a way to reduce it to something you already know. We know Fermat's little theorem if n is a prime. Let's apply it twice, once with the prime P, once with the prime Q. When we apply Fermat's little theorem, we have to choose a number relatively prime to P. And the cleverness is for the first case, when we're using the number P, we choose our number to be a to the Q minus 1. Since a is relatively prime to P, so is any power. And the second time when we use the prime Q, we will apply Fermat's little theorem with the number a to the P minus 1. And so when we do this, well, by Fermat's little theorem, we take our number a to the Q minus 1, we raise it to the P minus 1 power, and we get 1. So it's equal to the hour 1 on a clock with P hours. For the other one, we have a to the P minus 1, we raise that to the Q minus 1 power, and we get 1 on a clock with Q hours. What do you notice about those two equalities? So what do you notice about those two equalities?
The left-hand sides are the same.
Yeah, the left-hand sides are the same. And in fact, it's exactly what we want to study for Fermat's little theorem. Yeah, we wanted to study a to the P minus 1, Q minus 1. And so by choosing cleverly and applying Fermat's little theorem with a prime power twice, we have exactly what we want. So that means this number is 1 mod P and it's 1 mod Q. So when you divide by P, it has a remainder of 1. When you divide by Q, it has a remainder of 1. We want to show that it has 1 as a remainder when you divide by PQ. And so there's a couple of ways you could do this. Well, the first is, well, if it has a remainder of 1 when we divide by P, I can write it as 1 plus a multiple of P. If it has a remainder of 1 when we divide by Q, I can write it as 1 plus a multiple of Q. And what I want to do now is show that either Q divides alpha or P divides beta. And then that would show that it's equal to 1 on a clock with PQ hours. Well, since these two are the same, I can subtract 1 from both sides, and I get alpha P is beta Q. But since P and Q are different, P doesn't divide Q, so P must divide beta. Q must divide alpha. And we're done. So it's a really nice math concept of reducing a hard problem to a simpler one. Now, why do we care about this? This is one of my favorite applications in all of mathematics. It's one of the strangest. So imagine we have two numbers a and n that are relatively prime, and we calculate a to the n minus 1, and it's not equal to 1. Then we know n cannot be prime. Because we just proved if n is prime, then phi of n is n minus 1, and we proved that a to the n minus 1 is 1 if n is prime. If it equals 1, then n might be prime, we don't know. Is the number 91 prime? So 91 is a famous number. It is the smallest composite that looks prime. Any thoughts what goes into 91?
7.
Sorry? So what goes into 91?
7.
7. We're not really good at, we don't have a good rule for 7. I have seen the rule for 7. The rule for 2 is nice. If the last digit is 0, 2, 4, 6, 8, it's a multiple of 2. The rule for 3 is nice. If the sum of the digits is a multiple of 3, then the number is a multiple of 3. There's no good check for 7. But how did you prove to me that 91 was composite? You gave me a factor. Typically, the way we show a number is composite is we give a factor. What's wonderful or annoying, depending on your point of view of Fermat's little theorem, is it just tells you the number can't be prime. It doesn't tell you any factors of the number, just that it can't be prime. This is a little bit annoying. What do you mean you can't give me a factor? It's just, if it were prime, this relation would be true. It's not true. So you can use this as a little bit of a primality test. If a number passes this test, it's likely to be prime. And the more tests it passes, the more likely it is to be prime. But if it passes all the tests, that is not enough to prove that it's prime. And there are certain numbers that are called Carmichael numbers. They're composites, but they will always pass this test. And there's a lot of great stuff that's known about them. And what I like about this is it's a great warning to students that you have to be careful, that there can be catastrophic alignments. So this was the first unit from Fermat's little theorem. This was the worst of the 3. Any questions on this part? Okay, I'm going to just stop this as this is a nice unit, and then we'll do fast multiplication. So I will log off and then log right back on so I can save the recording.